Lab 4 is about oscillations of a mass spring system. So in this lab, we need to construct a computational model as well as an observational model of the motion of the mass spring as it oscillates. We also are going to be creating energy graphs that are plotting changes in kinetic energy, gravitational potential energy, and spring potential energy. And throughout this lab, we'll be consistently using the energy principle in order to calculate these changes in energy. We can also assume that since we know the surroundings do no real work on the system, that the total energy change of the system is also going to be equal to 0. We also need to apply a few kinematic equations that we can derive from Newton's second law to predict the motion of mass by using potential and velocity update formulas, and also apply some kinetic and potential energy formulas to calculate the changes in energy throughout the system. Our observational model just shows a video of the spring in which it moves in an arc motion as it hangs vertically. The x position and y position graphs are to the left and describe its motion in each respective direction. Now our main results when we put this into an energy versus time graph shows us that our total change in energy is equal to 0 as it plots a horizontal line, and that our changes in kinetic energy and potential energy are opposite in sign where they oscillate, meaning that their end behavior is different at different crests and troughs. So our observational model and predictive model give us two different graphs of the x position and y position. Now in the x direction, we see that they plot very similarly, although the experimental model has a much rougher curve and shows a faster motion in the x direction. However, in the y direction, we see that the experimental has far greater motion in the positive y direction. And we can actually pinpoint this source of error to possible inaccurate centers of mass in our tracker analysis, and also that we did not input all of the forces and energies that are acting on the system or affecting it in total. In our computational model, where we get into creating our code and glow script, we need to identify our initial conditions, which includes understanding what the mass is, our initial position vector, and our initial velocity vector, which we define here, and also our delta t, which in this case we define as a multiple of time between the time frames in our tracker analysis. We also need to define a few constants for our code. We need to define the gravitational constant near Earth's surface, which we're going to use 9.8 meters per second squared, the spring constant, and the relaxed length of the spring, which we derive from pre-lecture videos. Thank you, Professor. And also we need to define S. And we know that S is the magnitude of L minus L naught. We already have L naught defined, so we also need to define L and L hat. L is equal to the ball's position minus the spring's position, and L hat is equal to L divided by its magnitude. We also need to define at lines 94 through 97 the energy formulas for kinetic, gravitational potential, and spring potential energy, which we do and input the values that we've already defined, and also set our total energy equal to 0. Now in our calculation loop, we also need to define the net force and set the initial energies equal to their final energies. Now our net force is the sum of the spring force plus the gravitational force. We set our gravitational force equal to 0, negative mg0, since it's near the Earth's surface. And we set our spring force equal to negative k times s times L hat. And we just, at the bottom where we have lines 130 to 132, we just do some iteration of what we had for the spring earlier in our initial conditions. And lastly, we also need to calculate the energy changes. So we need to define delta K, delta UG, delta US, and delta E, which we do at lines 137 to 145. And we just do some reiteration of the formulas that we previously saw. So what does it mean? So throughout this lab, we apply the energy principle, but do we know that it's satisfied from this graph? And the answer is yes. Is because the energies acting on the mass spring system are all equal to 0, because where they're oscillating, we also know that they are opposite in signs. And because these opposite signs are able to cancel out, this ends up summing up to 0. And we also wanted to estimate the oscillation periods between the x direction and the y direction. So we want to use two different sets of data to define this. So for the x position data, we find that its average oscillation period is about 1.614 seconds. And for the y position data, we find it's about 1.551 seconds. And the difference between these estimates is actually important, because we can see that as we derive the formula from t equals 2 pi times the square root of m of the mass divided by the spring constant, that when we rewrite it in terms of the spring constant, how t can affect that value. So with the different values that we get from the x position data and the y position data, we understand how the spring constant value can change and also affect the spring potential energy and spring force acting on the system. So in conclusion, the energy principle can be applied to understand the sum of energy acting on the system. We also understand the conservation of energy, in which it is never created or destroyed. We also understand how a mass moves in a spring system when it's oscillating. As total energy can equal zero because the signs of energy changes cancel out, which we saw in our graph where we had potential and kinetic energy canceling each other out. And we can also continue to use Newton's second law to predict position and velocity, and thus also an object's motion.